everyone, I am Sheikh from Department of Mathematics, Pune College of Arts, Science and Commerce, Pune. I welcome you all for this presentation on Introduction to Graphs. In this video, we are going to see basic definition, notation and examples of a graph. Then we will see degree of a vertex and a theorem related to it. Finally, we will solve some of the examples to verify our topic. So a set of points and a set of lines connecting some pairs of points is called a graph. Going back to history, the town of Königsberg in Russia was divided in 4 districts by the river Prigel and 7 bridges connected by these 4 districts. The citizens were curious to know whether it was possible to start from some location, walk through all the bridges exactly once and return to the starting point. In 1736, the Swiss mathematician Leonhard Euler, the father of graph theory, answered the problem by representing the 4 districts by points and bridges by lines connecting this point. And this is considered to be the first theorem of graph theory. So graph theory is the study of graphs, which are mathematical structure used to model pairwise relation between objects. In this context, it is made up of vertices, which is also called as nodes or points, and they are connected by edges known as lines or links. Graph theoretical concepts are widely used to study model various applications in different areas. They include study of molecules, construction of bonds in chemistry, and the study of atoms. Similarly, graph theory is used in sociology, for example, to measure actors' prestige or to explore diffusion mechanism. In computer science, graphs are used to represent networks of communication, data organization, computational devices, and the flow of computation, etc. It is not restricted to this only. Many practical problems can be represented by graphs, emphasizing their application to real-world system. The term network is sometimes defined to mean a graph in which attributes, for example names, are associated with the vectors and edges, and the subject that expresses and understands the real-world system as a network is called network science. As far as mathematics is concerned, graphs are useful in geometry and certain parts of topology, such as knot theory, algebraic graph theory, which has close links with the group theory. Algebraic graph theory has been applied to many areas including dynamic systems and complexity. So with this brief introduction about history and application of graph theory, let's get started with the actual learning of introduction of graphs. Let's begin with graph terminology. Graphs are discrete structures consisting of vertices and edges that connect these vertices. There are a number of definitions available for the graphs given by several authors. We'll see the following definition, in which a graph consists of 2 sets, capital V and capital E. Capital V is a non-empty set of vertices, sometimes we call it as nodes, and capital E is a set of edges, where each edge, small e belongs to capital E, is associated with an unordered pair of vertices V1 and V2 belongs to capital E. We see the following diagram where capital V is equal to small v1, v2, v3, v4 set of vertices, and capital E is small e1, e2, e3, e4 set of edges. So these are the standard notations to denote the vertices, vertex set and an edge set. And we use notation capital G to denote the graph, and if you have more than one graph, we use G1, G2 like this. So these are the notation to denote the graph. We can observe in the following diagram, there are 4 dots that is, or points you can call, which are labeled as V1, V2, V3 and V4. These 4 points are known as vertices. So V1 is one vertex, V2 is also a vertex, V3 is also a vertex, and V4 is another vertex. A line segment joining these points, we can see here this is E1, from V2 to V4, E2, E3 and E4 here. So these line segments are known as an edges. So here we have E1, E2, E3 and E4. There are 4 edges in this graph. One more thing we observe here, capital V is given as a non-empty set. So set of vertices should be non-empty and set of edges could be an empty set. So we should have at least one vertex in a set of vertices. So we take suppose V1, this is the only vertex, or we take one more vertex, that is V2, and capital E we take as an empty set. We denote empty set by phi. So we have two vertices V1, V2. So this diagram is also known as a graph. So even if you have vertices, that will enough for us to become a graph. Now next move on to the next example. This diagram consists of 6 vertices and 7 edges. We see that two vertices small u and v in a graph G are called adjacent in G if u and v are endpoints of an edge small u belongs to G. So in this diagram v1 and v2 are adjacent vertices. Here this v1 and v2, this one and this one adjacent. v1 and v4 are not adjacent. Similarly v3 and v5 are not adjacent, but v3 and v4 are adjacent vertices. And we see that such an edge small e is incident at these vertices u and v, or sometimes we call an edge is associated with vertices or connected with vertices v1 and v2. Two edges are associated with the same unordered pair of vertices are called parallel or multiple edges. So in this graph we see that between v1 and v3 there are two edges, E4 and E5. So these types of edges are known as parallel or multiple edges. An edge associated with the same vertex is called a loop. So you observe here E1, which starting and end points of E1 is same, that is vertex V2. That's why E1 is known as a loop. So E1 is a loop and E4 and E5 are parallel edges. Okay, is it alright? Now we'll move to the next important topic, that is degree of a vertex. So the degree of a vertex V in a graph G, V, is the number of edges which are incident with it, and it is denoted by DEG of V. So degree of the vertex is denoted by DEG of V. Sometimes we denote this as D of V also. Okay, degree of V is denoted by D of V. Some other use this notation, or DEG of V. Both we can use. As a remark, you see every edge of the graph G contributes 2 degrees, one at each end vertex. Moreover, the loop at the vertex contributes 2 degrees at V. Example, we take graph V1, V4 and V5. Let's join this by an edge. That's fine. So let's consider this graph. We write here these degrees. Start from degree of V1. So there are two edges associated with V1. So degree of V1 is 2. Then degree of V2. There are 3 edges which are connected with V2. So degree of V2 is 3. Then degree of V3. There is only one edge connected at V3. Degree of V3 is 1. Then degree of V4 is 4 edges associated with V4, degree of V4 is 4 and degree of V5, that is 2. So this way we can calculate the degree of a vertex in a graph. So a vertex of degree 0 is called isolated vertex, and a vertex of degree 1 is known as a pendant vertex. So in this graph, V3 has degree 1, that's why V3 is a pendant vertex. And suppose we take one more vertex, V6, which is not associated with any of the vertex in a graph. So its degree is considered to be 0. Degree of V6 is 0 and V6 is known as an isolated vertex. So this way we have the concept of degree of a vertex. So we'll see one example based on this. Consider this example. Find the number of vertices, number of edges and degree of each vertex in the given graph. Identify all the isolated and pendant vertex. So in this graph, the vertices and edges we have to find and degree of each vertex. So first we'll label these vertices. You can start from any point and you can start from any vertex here. We start from here, so we call it this V1, V2, then V3, V4, V5, V6, V7, V8 and V9. So there are total 9 vertices in this graph. Now next we count the number of edges starting from here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. So there are total number of edges are 15. So we write a solution. Total vertices in this graph is equal to 9 and total edges is equal to 15. Now let's write degree of each vertex starting from V1. Degree of V1, as you can see, there is no edge which are incident at V1, so degree of V1 is 0. Then degree of V2, so we observe here 3 edges incident at V2, so degree of V2 is 3. Degree of V3, there are 3 edges incident at V3 and loop counts 2 to the degree, so there are 2 loops and total degree is 7. Similarly, you can write degree of V4 as 4, then degree of V5 as 1, then degree of V6 is equal to 3, degree of V7 is equal to 7, then degree of V8 is 4 and degree of V9 is equal to 1. So hence this way we can write the degree of each and every vertex. Now the next part is we have to identify isolated and pendant vertices. So we know that isolated vertices are vertices of degree 0. So here V1 is an isolated vertex and pendant vertex in degree is 1. So V5 is of degree 1 and V9 is of degree 1. Hence vertices V5 and V9 are pendant vertices in this graph. Now next move on to the next important topic, that is handshaking lemma. The handshaking lemma states that in a graph G, V, E, which is an undirected graph, so we have a directed graph also. in which every edge has some direction that we are going to see in the next video. So let G V comma be an undirected graph with m edges. The total degree of a graph of a vertices in a graph G is equal to twice the number of edges. If this is always be an even number, that is total degree of a graph is 2 times the number of edges in a graph. The result is applicable even if the multiple edges and loops are present in a graph. So let's try to understand this handshaking lemma with an example which we have already done. So in this example, the number of vertices are 9 and total edges are 50. If you count the total degree, means addition of degrees of all the vertices, that is 3 plus 7, 10, 14, then 15, 18, then 25 and this 5, 30. So total degree in this graph is equal to 30. Total degree is equal to 30, which is equal to 2 into 15, that is number of edges. So hence this lemma is verified here, that is total degree in a graph is equal to twice the number of edges. Now let's move to the exercise part. We will solve some of the example based on the topic we have seen. Here we do 4 examples. First one is draw the graph of the following chemical compound, the CH4 and C2H6. So considering carbon and hydrogen molecules as vertices and the bond between them is considered as an edges, so we can simply draw CH4 considering the C, H and edges between them, bond between them by these edges. So this is a graph for CH4. Another example, second one is give an example of a graph that has no odd vertices. We can draw plenty of examples. So consider first one. You can take here vertices V1, V2, V3 and we draw an edge between these vertices. And this way, you can observe here the degree of each vertex is 2, that is an even number. So consider third example, determine the number of edges in a graph with 6 vertices, 2 of degree 4 and 4 of degree 2. So for this we take 6 vertices and join these 6 vertices by an edge. This is first one, then from this vertex we draw here, from this vertex here, and again we join this vertex here, then these vertices are joined, these 2 vertices are joined to this vertex, okay, and that's it. So you observe here these 2 vertices of degree 4 and these 4 vertices of degree 2. This way we can draw a number of graphs of this type. The fourth example is to verify handshaking lemma. For this graph, you can verify this as we have done earlier. Take the total degree of vertices in a graph. This should be equal to twice the number of edges. You can verify by adding all the degrees of this vertex. So with this, we'll end up with the presentation. I hope that you have understand this. Thank you.